Good afternoon, everyone. So my name is Hussam Abdi Mukhtar. I'm assistant professor from University of Dubai. Today I'll be talking about a project which we have started almost 1 year ago. It's about a secure and robust wireless communication system for low latency applications. It's basically a physical layer security system which improves the transmission efficiency also. Not only we add embedded security, but also we improve the transmission efficiency of wireless communication system. This project is part of the Wireless Communication Research Lab at University of Dubai. The team members includes members from University of Dubai, and we have also collaborator from Khalifa University. Currently, we have 3 research assistants working in the Wireless Communication Lab. The outline of this presentation is as shown. First, I'm going to introduce the topic. I'll describe the system. I'll give an overview of the physical layer security system. I'll show some of the performance evaluation results. I'll show also video demonstrations of the system. We have tested the system using simulation, and also we have implemented the system using software-defined radio. So I'll show you some results obtained in the lab. Then finally, I'll provide some conclusions and describe future work. So as we all know, wireless communication is a key enabling technology for many applications such as remote health monitoring, connected autonomous vehicles, mobile phone networks, and many others. However, wireless communication is fraught with several challenges. We have limited bandwidth in wireless communication networks. They also suffer from errors due to noise, interference, multipath fading. And also they are vulnerable in terms of security because of the broadcast nature of wireless communication system. Physical layer modulation techniques are used to overcome some of these challenges to enhance the transmission efficiency and the robustness of the communication systems. In this work, we exploit these modulation techniques to provide embedded physical layer security, in addition to enhancing the transmission efficiency. Compared to higher layer conventional crypto systems, physical layer security systems, they are less computationally complex, relatively. They also considered faster. So the higher layer crypto systems, they are relatively slow for high-speed communication. They also reduce the operation time for energy-limited devices, battery-powered devices such as IoT sensors, for example, and they are vulnerable to jamming. Here we consider orthogonal frequency division multiplexing. This is a standard modulation format which is used in most wireless communication standards currently, like in LTE, Wi-Fi, and WiMAX, and also in DVB and power line communication. So it's a very well-known modulation technique. We modified this modulation technique by introducing a time domain interleaving. I'll show a demonstration of what I mean by time domain interleaving. Basically, by introducing this time domain interleaving, we improve the robustness of the communication system. Robustness, here we measure it using the bit error rate, for example. We also provided a low complexity physical layer security. How did we do that? I'll show what I mean by embedded physical layer security, but this is a system overview. It shows, so our system basically, these are the benefits obtained from using our system. So we have immunity against eavesdropping, because we use actually scrambling using a secret key, and an eavesdropper cannot listen. If an eavesdropper trying to listen to the communication, he or she will not be able to decode the signal. Also, it's immune to jamming because we are using time diversity and frequency diversity. So if a jammer jam one frequency, the receiver can still recover the signal from other frequencies, because we spread the information across multiple frequencies. Again, also in terms of signal strength, because we reduce the bit error rate and the SNR requirement, the signal to noise ratio requirement, we increase the signal strength. And we also save in terms of power. So we improve the power efficiency. Actually, we, based on our analysis, it's about more than 90% in power saving. In addition, of course, to the embedded security. So this is the architecture, system architecture of an OFDM system. These are the main building blocks. It's not necessarily to understand each block, but the upper blocks, these are the transmitter, and the lower one is the receiver. Basically, we do some operations in the transmitter and the inverse operations at the receiver. So this is the standard of the M system, the modulation technique. This is the difference here. This is what we added. We added just a block after the what we call the IFFT. IFFT is basically spreading using multiple carriers, sub-carriers. We spread the signal over multiple frequencies. And then after that, we go to the time domain and we do what we call time domain interleaving. Interleaving is basically scrambling the samples using a secret key. So that interleaving is done using a secret key. At the receiver side, we do the interleaving using the same secret key. So this is the standard of the M. I'll go over this quickly because we're not interested in the of the M. Okay, so this is the time domain interleaving part. Notice the each frame, each column we call it an OFDM frame. So each OFDM frame is scrambled using a secret key. We call this time domain interleaving. At the receiver side, we do the inverse operation. You will not be able to decode the signal unless you do the interleave using the secret key. Okay. Of course, notice here in this, we are doing scrambling within one of the M frame. We can also do scrambling within multiple of the M frames. So we call this the interleaver depth. If you do the scrambling within one of the M frame, so interleaver depth is one frame. You can consider interleaving across 3 or 10 or 256 columns, and then you will have a longer interleaver or interleaver depth equal to the number of columns. Okay. Of course, as you increase the number of frames involved in the scrambling, you will pay the price in terms of latency, delay, because at the receiver side you will have to buffer because you need to receive multiple columns. Then you do the inverse operation, which is the interleaving. Okay. In terms of security, here I just explained what we mean by interleaver length. In terms of security, it's equal to n multiplied by interleaver length. So n is the number of samples in the OFDM symbol. So if each column is 256 samples, and nd is how many frames. If you consider one frame, then it's only nd is equal to 1. So your the security is proportional to n multiplied by nd factorial. Okay, so if you consider n equal to 256, you will need to perform 2 to the power. You will need to perform 256 factorial, which is more than 2 to the power 1683 trials, which is not practically. It's practically infeasible to break the system using exhaustive search. In terms of performance, transmission efficiency, here I'm showing the graphs, the bit error rate performance with respect to the signal to noise ratio. The black line over here is the standard of the M system. And this set of curves is using the time domain interleaving for different interleaver depth. Notice the big improvement in the SNR over here. It's around 14 dB at 10 to the power minus 4. We have 14 dB. 14 dB is actually significant. It corresponds to more than 90% in terms of power saving. By introducing this time domain interleaving using a secret key, we did not only introduce security, but also it helped us improve the system, the transmission efficiency and robustness. Increasing the interleaver depth, we did a study for low mobility applications. Low mobility applications, considering a car moving less than 40 kilometers per hour. Increasing the interleaver depth does not improve the transmission efficiency or the bit error rate performance. However, for high mobility applications, as we increase the interleaver depth, we improve the performance. So we can achieve further improvement at the expense of latency, delay. Why is that for high mobility we have this and for low mobility we don't have it? It's basically because our system exploits frequency and time domain diversity. For low mobility, you can say that there is no time diversity. The channel does not change within an interleaver block, the interleaving block. That's why we cannot achieve improvement if you increase your interleaver depth. But for high mobility, the channel varies fast, quickly, compared to the OFDM length, block length. That's why we have time diversity. That's why when we use our system, we manage to obtain additional performance improvement by increasing the interleaver depth. Okay, so it would be wise to know the application. Based on the application, we can select the interleaver depth. Okay, so this is a summary of the obtained results. We have also implemented the system using RF prototyping hardware, basically software-defined radio. This is the setup in the lab. We have a transmitter and a receiver, each one connected to a laptop. We did measurements indoor and outdoor. I'll show a video demonstration. This video shows the setup. So this is the transmitter side. We are transmitting an image using 4QAM. 4QAM, the 4 constellation points corresponds to a modulation technique. We call it 4QAM. At the other side, at the receiver, we managed to receive the signal successfully. You can see that we have 4 points, which is also the modulation technique, however, with some noise. But as long as they are distinguishable, then we can decode the signal correctly. Here we are using the correct key. However, if an eavesdropper trying to listen to the signal, we are simulating this by using an incorrect key, the signal will be a noise signal, and he or she will not be able to decode the image or the transmitted signal. This video, I think it shows the same thing. Here we are trying with colored images. Again, this is like a graphical user interface. You load the image. You transmit the image. Of course, we implement time domain interleaving using a secret key. At the receiver, we run the receiver. We expect to receive the signal. Okay, we have successful constellation points indicating successful reception. And after some delay, we receive the image. Here we are sending uncompressed image. That's why it took some time, because one of the applications for this satellite imaging, they use uncompressed images. Here, if you change the key, if you use incorrect key, then the signal will be a noise signal, and we lose the image. You can see some traces maybe of the original image, but I think this is because rendering of the software. And also we can improve this by increasing the interleaver length. We can do further study actually for that. So as a conclusion, we developed a physical layer security system based on time domain interleaving. For OFDM-based communication systems, the performance of the proposed technique was studied using theoretical analysis, simulation, and also real measurements using RF prototyping hardware. The obtained results showed that substantial improvement can be achieved in terms of the transmission efficiency with embedded security. Choosing the interleaver depth depends on the application. For low mobility applications, there is no point of using long interleavers. However, for high mobility applications, we can benefit from the interleaver by increasing the interleaver length. As a future work, we have participated in a call for research, and we have won a prize, a grant, research grant of 350,000 AED to implement the system in a product. And this product should be used in one of Dubai government institutes. This project was funded by Dubai Electronic Security Center. So we are doing the prototyping, and our goal is to produce a product at the end which can be deployed easily. You can plug it in your laptop and use it. These are some of the relevant publications if you are interested to know more details about the project. So thank you, and I'll be happy to answer your questions.
Thank you, Usam Mulden. Who has any questions about the talk? Nobody in the room, so then I may have some questions. So you were talking about the key. Is it a shared secret or a public-private key implementation?
The shared key, but we can use asynchronous key. So you can encode using public key. You can encrypt using public key, and then you decrypt using your private key. So, but in our experimentation, we are just using a shared, pre-shared secret key.
Pre-shared secret key. Okay, cool, cool, nice. Any questions from the room? Yeah, we have one.
I don't have a question. Just I want to know if this product can be in the market.
Currently, still it's in the prototyping stage.
Yes, after
that, this is what we hope to. Yeah, we hope that we at the end of this project we come up with a commercial product.
Good luck, and it's a very good idea.
Thank you.
Thank you.
Thank you.
Very good talk.